All right, class. We're doing circular motion with a focus on quantitative calculations of centripetal force, centripetal acceleration, and such. We have done these first three sub-objectives from objective 3. The next one we're going to do is draw a vector diagram relating initial velocity, final velocity, and change in velocity. It's going to happen a little bit later. We're going to start with describing circular motion in terms of period, frequency, angular velocity, and angular displacement. That's going to be the first part. So once we do that, once we are able to identify these different variables, then we can also move towards actually solving problems involving centripetal acceleration and circular motion. We're going to calculate all relevant forces or component forces that produce circular motion. So other than from last class just identifying it, we're now going to calculate those forces and calculate a net force. And then we're going to combine Newton's second law with circular acceleration or centripetal acceleration to again, problem solve. So first up, we're going to look at this GIF, which make sure it's working, where we have two, I don't know what they are, rodents. I'm not even sure if they're real, but two rodents going around a circle on a record. And I asked the question, between these two rodents, what is the same and what is different? So we should be able to identify that what is the same is the time period of one whole rotation or revolution, right? If we were to think of start and stop, they both complete one full revolution in the same time. So our time period is going to be the same, and therefore our frequency is going to be the same. Now what is different? And this is a little bit harder to see, but they're on different, they're at different radii, different radiuses. And since they're on different radii, they will have traveled different distances as they go around the circle. Because we know that of a circle, the circumference is equal to 2 pi r. So what is different is their speed that they're traveling. And I'm going to have to give that a different name. It's not just speed, because we have to think of a linear and angular speed. So this is linear speed. Because what we're going to find out is they have actually different linear speeds due to different distances traveled, but the same angular speed because of the same time period or frequency. So in this linear velocity picture, or a picture representing an object in linear velocity, let's imagine that it started at this red dot and it moved in this direction around the circle. If we were to identify the distance that would have traveled, well, it travels a full circle or a full circumference of 2 pi r, and it travels it in some time period. So down here, our linear velocity is v. We're still looking at the units as meters per second. And we know that v is equal to distance over time, or rather the change in distance over the change in time. And the red, if they both have the same time period, they take the same amount of time to travel one full rotation, the red rodent would travel less distance than the blue rodent. So we know that that's proportional to the radius. And so that is 2 pi r, which is the distance from one full revolution, divided by the time period, which is the time of one full revolution. So both of these, delta s over delta t, or since it's moving at a constant velocity, we can use 2 pi r over t. And that you'll just have to remember, that's not in your data booklet. But when we go to angular velocity, when we see the word angle, then we need to start looking at values that represent angles. And one thing that's different is that normally in the past we've used degrees to represent angles, but when we talk about circles, we like to use 2 pi, and that's because when we looked at sine graphs, cosine graphs, things like that, we tend to follow a units of radians. Now, I recognize that you might not have the best experience with radians, so just know that you can always have degrees in your mind and say that 360 degrees is the same thing as 2 pi radians. And what you want to focus on is just the difference in, we're just converting here. So that means that 180 is the same as pi radians. And so whether you're traveling one full circle or 360 degrees, it's the same thing as saying you're traveling one full circle as 2 pi radians. And so then instead of meters per second, we need to look at this as radians. Well, let me put that in a bracket. Radians per second. So how much angle has occurred per unit time. And the symbol we use for angular velocity is this omega. So if we looked at this red rodent, it traveled this distance and this angular distance. So theta is your angular distance or angular displacement. So similar to when we had distance over time and linear velocity, where linear distance is s for like distance, it might be delta d. In angular velocity, we're looking at omega is equal to the change in the angle divided by the change in time. And again, similar in linear, when we said, it's easy if it's moving at a constant velocity, is if we use the full circle, since we can calculate or we can measure the time period of that revolution. We're going to do the same thing over here. We're going to identify how long does it take to travel 2 pi radians. Well, it takes one full time period. And this is your equation for omega. So omega is equal to 2 pi over t. You might also see this as recognizing, hey, I know what frequency is. Frequency is 1 over time period. So this is also saying this is 2 pi f. And that's going to be in your data booklet. Omega is equal to 2 pi f is in your data booklet. And now let's compare these two. If I look at my linear velocity, I have a 2 pi divided by t times r. Well, 2 pi over t is omega, and so I can plug that in and say, you know what, v is omega times r, and this is in your data booklet. In unit 6.1 or topic 6.1. All right, so when looking at these two rodents, we're recognizing that there are things that are constant and things that are different. Things that are same and different, and that is a time period. Since it has the same time period, they both have the same angular velocity, but since they have different radii, then they have different linear velocity. And we're going to look to see where we can apply these two equations into future examples. So let's start with going into, are they really accelerating? What does acceleration mean? Well, acceleration is equal to the change in velocity divided by the change in time. And are they changing their velocity? Well, hint, hint, velocity is a vector, which means it includes direction. And these two rodents are definitely changing their direction. They may have constant speed because we're looking at uniform circular motion, but they have they're changing velocities. So let's look at these velocities in a circle. At time 1, you have some initial velocity, u, and at time 2, you have some final velocity, v. It's traveled some angular displacement theta in some unit time. And even though their speeds haven't changed, their velocities have. And this brings us back to Newton's first law, where I want to identify something that we've kind of excluded to make our life easier, but it's going to be needed to be brought back. Newton's first law states an object in motion stays in motion. And what we did not say is an object in motion stays in linear motion unless acted on by an outside force. When you roll a marble, it rolls straight. It doesn't curve, it doesn't turn unless there's a force pushing it left or right. So like going down a hill or something. So that means that the object wants to stay in some linear path, and in order to apply, or in order for it to move in a circular path, it needs a force acting towards the center. So it needs to have an acceleration acting towards the center for it to change its direction. Notice that u and v are not changing their magnitude of their velocity. So they're not changing their speed. That means that the acceleration is not pushing it forward, not slowing it down. It's just changing its direction. And that's why it's acting perpendicular to the direction of motion. So we're looking at acceleration, which is a change in velocity divided by some change in time. So to compare these two velocities, there's one way that you can do it is let's just look at what happened from the initial to the final velocity. So I'm going to draw them on top of each other. I'm going to first draw, I'm going to do my initial velocity u, and then let's make v red. And I'm going to make my final velocity go out. And I tried to make them equal. And notice that the change in the velocity, the difference between u and v, is a vector which represents the change in the velocity. This represents the average change in the velocity between time 1 and time 2 as it goes from initial velocity u and initial velocity v. And you might see a relationship here of look at the direction of this change in velocity and look at the direction that I drew this centripetal acceleration acting towards the center. They're both acting in the same direction because halfway through time 1 and time 2 you should see this average acceleration. So that's just kind of helping us identify the direction of the centripetal acceleration, but I'm not exactly going to derive it. I'm not going to solve for it. I'm just going to give it to you. And that is that the centripetal acceleration is equal to v squared over r. Where that comes from, some derivation. If you want to Google how to derive centripetal acceleration, I think it's possible to understand, but it's unnecessary. Going forward with this, I can say, you know what? I have an centripetal acceleration. Let's apply Newton's second law and try to find our centripetal force. Well, that's just m times v squared over r. So that's mv squared over r. Both of these are in your data booklet. Now recognize this v is a linear velocity. So you can also go further. Let's just move this over because you can go further and say, well, I do know that v is equal to omega times r. What if I plug omega r into there? Well, I get omega squared r squared over r, and that cancels out to give me omega squared r. So my centripetal acceleration is v squared over r as well as omega squared r. There's some really important parts of that, knowing that omega doesn't rely on r. It's not proportional to the radius, where v is proportional to the radius. So you might get tripped up with that, saying which one has a larger centripetal acceleration, and you cannot use this equation because v is proportional to r. So it's best, this one is like my favorite of all because it only involves the time period is in omega and the r is outside of omega. Similarly, you can use this and say, you know what? I can plug in the omega squared r as centripetal acceleration, and I can find it to be m omega squared r. So these two equations, fc is equal to mv squared over r is equal to m omega squared r is good, and then ac is equal to v squared over r is equal to omega squared r. That's also really good. That's all in your data booklet. So let's just make sure we've identified all the terms that you'll need to know. And that is one time period, right, which is t. We already know that. Let's give it a frequency, which is f, which we know f is equal to 1 over t. Linear velocity, which is v, and that's just v is equal to 2 pi r over time period. Angular velocity, well, that's omega, and omega is equal to 2 pi over time period, or 2 pi times the frequency, since frequency is 1 over t. Centripetal acceleration, which is just a sub c, which is equal to either v squared over r or omega squared r. And then centripetal force, F sub c, which is equal just to mv squared over r or m omega squared r. So these are all the equations we will be using in this whole unit. Yeah. Recognize that although we have an equation for centripetal acceleration and centripetal force, that centripetal force is composed, right? This is other forces. Other forces compose centripetal force. This could be gravitational force, it could be normal force, it could be tension force, it could be frictional force, right? It's not a real force. A centripetal force is the net inward force. Net force, and really just inward, because if it's outward, it's not in some circular path, right? Where we'll see some of these examples are in, so the same ones that we used. We've already identified what net force exists, what components of forces are forces that produce circular motion. All we're going to do now is apply those variables, those net forces that we found, into these equations that I just gave you. So I'd like to do you're standing on Earth. So I'm going to pause this video and I'm going to give you some values that we're going to use to understand our gravitational and our normal force on Earth. All right, so I've given you the speed that we all travel as we're standing on this Earth because the Earth is rotating, and the radius of the Earth. So I would like to find out what normal force we feel while standing on this Earth. So our end goal is to get to some normal force. Now, before we said, hey, you know what? Let's see if I can do it in a bright color. We have a gravitational force and we have a normal force, and they're equal. But now I'm telling you, that's not completely true. They're very, 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 very close. So we just call them equal. But let's see if we can find out what difference, how negligible is it? So we need to first, and if you would like to pause this video and try to solve it, you can, but I'm going to walk you through it. So we need to first identify how we can get to some centripetal force, because we know that centripetal force, it's the same thing as the net force in or out, right? So in this case, the net force in or out is a gravitational force minus a normal force, because they're in opposite directions. I'm setting gravitational force to be larger, and there's a reason why, but if you could also do r minus fg, we would just end up with a negative somewhere. And this is equal to mass times r centripetal acceleration. I really think some level of this line is needed somewhere, recognizing that centripetal force is the sum of the net inward and outward forces, identifying the inward and outward forces, adding them together or subtracting them, and then setting that equal to the mass times the centripetal acceleration. Now, we have mg, we have r. Well, we don't have mass, so let's identify what's my mass. I don't know, I'm 70 kilograms. So you might need to know that. And that means that Fg minus r is equal to mass times my centripetal acceleration, which is v squared over r. And I have v. I have my velocity, my linear velocity. So let's plug this in. I got mass times gravity minus r. We still don't know what r is. That's what we're solving for. Equals mass times velocity squared over r. Let's solve for r. So I get mg minus mv squared over r is equal to r. Or little r is my radius of the Earth, because that's what I'm orbiting. That's what I'm rotating around, center of the Earth. So interestingly too, mathematically, I can take out the m's and I get this g minus v squared over r. And you can see this v squared over r, that's my centripetal acceleration. So that's like my change in my, that's my difference in my acceleration from my normal to my gravitational force. So okay, now let's plug some values in. 70 times 9.8 minus, and then we have to do v squared over r, 460 squared divided by 6.37 times 10 to the 6th. and that's equal to my r. So you can see this 9.8 is going to be much larger than 460 squared divided by 6.37 times 10 to the 6th. So let's do that. I have 460 squared divided by 6.37 times 10 to the 6th. So I get 9.8 minus, and this is where the negligible difference comes in, 0.0332 equals r. And so 70 times 9.8, that's my gravitational force, right? So I have 686 newtons downward. That's my gravitational force in newtons. And then I do 70 times my 0.0332. And this is technically my centripetal force, which is 2.32 equals R. So you can see that it is pretty much negligible. R is going to be equal to 686 minus that answer. I get 684, 3.7 newtons. I mean, of course, I'm allowing some level of precision. So it's actually, I mean, it's close enough, but there is some small difference, right? 686 is my FG, right? FG is equal to 686 newtons, and my R is equal to 683.7 newtons, or 684 newtons. So we have a 2 Newton difference. But that's interesting, huh? And so that's coming from, and this is a thought experiment. You can think about when you're spinning around the Earth. If the Earth were to spin so fast, and here's where I can stop you here in this video, and I want you to think up until next class. How fast does the Earth need to spin in order for you to not feel a normal force? How fast does the Earth need to spin, so it's my linear velocity v, so that you do not feel a normal force? That means you are orbiting the Earth. Like you can jump up, and when you jump up, you don't change heights, right? You just orbit the Earth. The next question you can go is how long is a day when you are traveling at that speed? Right now, our day is 24 hours. We're traveling at 460 meters per second around a radius of 6.37 times 10 to the 6 meters. If you do the math, right, 2 pi r over t, we should find the time period to be 24 hours. But how fast does the Earth need to spin in order for you not to feel a normal force, and how long is a day when that's happening? All right, take that, see if you can have some fun with that, and I will see you in class.